As you may know, there are at least 21 wild species of rice in the genus Oryza. And among those species, we have Oryza officinalis complexes, mostly composed of the CC genome species, in addition to the BB and DD and EE genomes. In these officinalis complexes, there are 3 diploid CC genome species, Oryza officinalis, Rhizomatis, and Archingeri. And here you can see the CC genome species showing very different phenotypes. And in CC genomes, there are many kind of useful and disease resistance genes. And especially for the CC genome, diploid CC genome species, they have a specific character of the very early blooming at the time of the day, and almost midnight before the sunset. So it's incredible character to use for the future breeding. So before, we have 81 accessions in our resource collections, and those are collected from almost all over the Asia. And however, the Oryza archingeri and Rhizomatis is distributed in the restricted areas. And Archingeri almost distributed in the central area of the Africa, and Rhizomatis is very restricted and only in Sri Lanka. So here you can see the many kinds of phenotypic characters and photographs in our Oryza race. And there are many specific characters for the CC genome species. So we'd like to sequence and uncover the genome structure and the specific functions in the CC genome. So before starting the CC genome species, we evaluate the genome size of 3 species. Using the flow cytometric analysis, we obtain the differences of genome sizes among 3 species. So as you can see here, the Oryza officinalis has about 50% more genome sizes than Oryza sativa, that is 570 megabase. And Archingeri shows a little bit smaller genome sizes, but about 40% larger than the sativa. And the Rhizomatis showed the biggest one, about 610 megabases. And we decided to use the Oryza officinalis. One is because the Oryza officinalis is the shows the widest distribution and in Asian countries. And the second reason is Oryza officinalis have been used to construct the back-end back libraries and already done the back-end sequencing by Rodwin's group. So we decided to use the Oryza officinalis as our typical CC genome and analysis. And using the Illumina short reads, and this shows you a very simple and method to how to assemble and how to complete the genome sequencing of the CC genome. So Illumina short reads we first analyzed, and using those short reads we assembled into the scaffolds. And after the scaffold making, we mapped on the back-end sequence arrays, which are almost already constructed by Rodwin's group. So mapping on the back-end sequences, we can get a little longer. Very well and characterized and genome sequences. But after that, we have to fill by using some longer sequences, such as 454 long sequences, to complete the pseudomolecules. So the informatics method, I'll skip details of informatics method. We just used a soft de novo assembling method program, and also the lay program and Platanus. Platanus is very strong for the heterogeneous genome construction, mainly developed based on the human genome analysis. This is a newly developed one and developed by the group of our institute. So the currently available reads we have the paired end 200 base 8-range sequences and the mate pair sequences for the 2.5 kb and 6 kb and 8 kbs for each. So the all map back-end sequences, we have already. So using these sequences and assembling program, we now have constructed the scaffold of N50 of 45 kb, and the number of scaffolds are the 56,000. So the total length of the of these scaffolds is the about 400 megabases. So this corresponds to the just almost the same size of the Oryza sativa genome. But as I mentioned before, the CC genome has almost 600 megabases. So we have to gather the more sequence reads. And in addition, we tried to use the Platanus program for assembling. So in this case, we could assemble the total length of about 5.3 megabase length, and this and also the showing the N50 scaffold and 137 kilobase. So this yeah, this seems a good result, but we haven't yet examined in details. So, if whether this Platons program will fit for our analysis or not, will be needed to examine more. So yes, so at the present status, backend supported super scaffolds. The Hajime is our informatician to construct the pseudomolecules. Hajime called this method BSSS, so B3S. So we call our scaffold and B3S. The mapping result of array assembly by Brad showed the total number of scaffold of 56,000, and the mapped scaffold number is 31,000. And this covers about 97% of the total length of the scaffold. So, and a mapped scaffold is very low, only about 2.5%. So the scaffolding could work very well, I think. So the mapped scaffolds correspond about 106% of the Nippon Valley genome. And this year, to test the pseudomolecule and result, using the chromosome 3 short-term sequencing result constructed by the Rodwin's group. So the x-axis shows the chromosome 3 CC genome short-term project, and X shows our pseudomolecule. Our y-axis shows our pseudomolecule. So as you can see here, the alignment of these two and the pseudomolecules are very well matched and make straight lines. Although there are many short indels and inversions still in this figure, but we think our pseudomolecule works very well at this moment. So the final result at the moment is a pseudomolecule of OO Oryza officinalis as of today. So OOIO map built 0.1 faster, total nucleotide number and without and with N arrays. They correspond to about 77% of the 570 megabase Oryza officinalis genome size. So the status is whole genome shotgun assembling of Illumina short reads created 45 kilobase scaffolds of N40, and a pseudomolecule covering about 77% of the genome was constructed as OOIO map built 0.1 faster. And finally, the created pseudomolecule contains about 10% N arrays. Thus, it seems to be covered about 70% of the CC genome. So I skipped the details of the informatics part. So please visit to the poster of Hajime, to the poster number 1. And after this, we have to fill gaps using relatively long sequences. And finally, we'd like to rebuild the draft genome at the OO-IO-map build 1. So related to our activities, we are simultaneously proceed as activities of 3 other activities. One is the construction of, the next activity is construction of pseudomolecules for itching jelly and rhizomatous. The other is generation of RILs, recombinant invalid lines, or the chromosome substitution lines for all combinations among 3 species. We have just started the crossing and generating the seeds. And the last one is taking over CC genome integration lines from IRI, from Dr. Burak. So, and together with all other wide integration lines to our National Bioresource Project Japan. So I'd like to thank all the collaborators here in our National Institute of Genetics Japan and also the IOMAP project. Thank you very much.